Right, say we had a matrix equation like AX is B, right?
Yeah.
So this is some matrix multiplied by some vector gives you some other vector, right? And one way I could solve this is I could just figure out what A inverse is and hit both sides with A inverse. And I could come up with, all right, X is A inverse applied to whatever the B vector is.
But it just says that A doesn't have an inverse.
Yeah, so this is what I would love to have happen.
Oh.
If A doesn't have an inverse, this is not an option, right?
Yeah.
And so how else do I do this? Like, what can I do and what do I know is going on? So how about the matrix doesn't have an inverse? What does that mean in terms of functions or something?
But it doesn't have an unfunction.
It doesn't have an unfunction, and the reason it doesn't have an unfunction is
It's not a function.
that it smashed something. It itself might well be a function, but it definitely smashed something, right? If it doesn't have an unfunction, it failed the horizontal line test, whatever the hell that means. In this case, that means it smashed something, okay? So what that means is that if I were able to conjure up a solution to this somehow, right? There are a couple options. So, how many cases are there?
One.
Solution finding. So if there's not an inverse, right, that means it smashed something. If I even thought about trying to find an inverse, that probably means this thing was square. Okay, see that? Although even if it's not square, this still applies. What are the cases?
Would there be two cases, one where there is 0 solutions and one where there is infinite?
Perfect.
If it were square, why wouldn't you be able to find an inverse?
If the determinant was 0. Like, for instance, if I had this matrix,
Rows that are proportional to one another.
1, 1,
Yes.
2, 2. Yeah. The other good guess was this one. Another good guess might be this one.
Okay.
But none of those have inverses. The reason none of them have inverses is that one of the rows is a multiple of the other row. That's just me writing down two equations that have the same information.
Okay.
Is that the 0 solutions case or the infinitely many solutions case? Okay. Yeah, that's the infinitely many case, right? Because what I'm writing down is I'm really writing down x plus y and 0x plus 0y, right? If these contain the same information, I don't really need the second one, so I have a which system? Under, over determined? Underdetermined because I have fewer equations than variables. You guys see that? So that's the infinitely many solutions case.
So the fact that there's 2 zeros makes that not relevant?
Yeah, the fact that there's 2 zeros there means that it's a scalar multiple of the first equation and it'll contain the same information. I don't have an opposite side for this, right?
But if it was 1, 1, and 2, 2, would it be the same deal?
Yeah, exactly. You guys see that? The other option is this 0 solutions case, right? And really, I suppose I should have augmented this because, yeah. Let me augment this. So, in this case, these two equations contain the same information. I should walk back a little bit of what I just said. These two equations have the same left-hand side, right? but the equations in this one contain the same information, right? They're x plus y is 1 and 0x plus 0y is 0. And then the other, they're x plus y is 1 and 0x plus 0y is 2.
And that doesn't make sense at all.
You guys see that? This one doesn't make sense at all, right? So I'm stuck in one of these two cases. And it's hard to tell which one I'm in. How could I try to tell? If I can't find the inverse, I want to know which one of these I'm in.
Or you can look at the dimension and see how many.
Good, that'd work, right? We could read off the number of equations and the number of variables. That'd work. We might have to worry about redundant equations a little bit. So,
Are you going to be making study guides for the tests?
probably.
Okay.
So what I want from you on this, right, is there's two cases, either 0 or infinitely many solutions. And the way I would figure out which case is which is what? What's your other tool for solving one of these equations? I already wrote it on the board.
Like right now.
Using variables?
Not inverses, not converting to variables.
Augmenting?
Yeah, I could augment and then try to get the identity matrix on this side, right? You guys see that? That isn't going to happen in a case where I don't have an inverse. But in a case where I get a statement that's true, always, right, where I get a row of zeros, that's an infinitely many solutions case.
Okay.
And in a case where I get a statement that's always false, that's 0 solutions.
So if you wanted to, I guess, you could try changing the bottom row to all zeros on purpose to see if they would all be zeros?
Yeah, so what it means that A doesn't have an inverse is that someplace in that process of trying to make the identity matrix on the left-hand side, you'll run into a row that's all zeros,
Okay.
on the left at least.
Okay.
If it's also 0 on the right, you're in this case. If it's 0 on the left and not on the right, then you're in this case.
Okay.
So can I help?
Yeah.
So the answer to their question is augment, comma, it's going to be messy. There's either 0 solutions or infinitely many solutions.
Okay. And how would you take an augmented matrix and turn it and add what is that called? The 1, 0.
So if I augment by identity?
Yeah. What would you do with the already augmented piece?
Oh, okay. You can't.
Okay.
So there are two processes. Either you're solving this equation or you're finding the inverse of the matrix. If I know that there isn't an inverse, there's no point in augmenting by the identity. That's probably how I figured out that there isn't an inverse.
Okay.
Does that make sense?
Mostly, yeah.
Okay.
Yeah, if that inverse kind of path breaks, then
Yeah, that process by which I find an inverse is going to break down in exactly the same way that this is going to break down. You're going to get a row that's all zeros. You're not going to be able to conjure up the identity on this side.
Okay.
You want to see one?
Yeah.